Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.3, Problem 1. This is Section 3.3, Problem 1. It says, Dan wishes to produce Terminator telephones and Mad Max answering machines. Each Terminator telephone uses 2 feet of wiring and 3 pounds of plastic. Each Mad Max answering machine uses 5 feet of wiring and 4 pounds of plastic. Altogether, there's 190 feet of wiring and 180 pounds of plastic. The telephones have a profit of $25 and the answering machines have a profit of $28. How many of each should Dan produce to maximize his profit? So, just to set up the problem, we have 4 steps, and then to solve the problem, there are 4 more steps. So to set it up, first, find your variables. The variables are always easy to find. It's the 2 things that are being made. So in this case, what are we making? We're making Terminator telephones and Mad Max answering machines. You can let one of them be X and one of them be Y. And you can use other variables. I always go to X and Y because when I get to the graph, it's more natural for me. Whichever one gets mentioned first, I typically turn into an X. So X equals Terminator telephones. Y equals Mad Max answering machines, and I'll abbreviate a little bit. So that's step 1 of 4 steps. Identify your variables. So we did, and it's the 2 things being made. Typically, that's not tricky. Next is find the object function. Look for information that's usually about profit, usually near the end. And this one's fairly typical. If you look near the end of the problem, it says the telephones have a profit of $25 and the answering machines have a profit of $28. So you want to maximize the profit. So what I'm going to do is I'm going to say maximize Z equals. So my telephones are represented by the variable X, and each telephone produces a profit of $25. So 25 times X plus, now the answering machines are represented by the variable Y, and each answering machine has a profit of $28. So that's step 2. Step 1, identify my variables, which I've done. Step 2, write out the object function, which I've done. I've found the information that's given about profit, which is near the end, which is typical. Now, step 3 is the step with the most work. Set up your constraints. So underneath maximize, I'm going to write subject to. And now in terms of the constraints, the limiting factors, what's going to limit the number of answering machines and telephones I can produce is the amount of wiring and plastic that I have. I have 190 feet of wiring, 180 pounds of plastic, and something's going to get used up first. It's going to determine how many I can make altogether. So my 2 limiting factors are the 190 on the wiring and the 180 on the plastic. So off to the side, let me write 190, and I'll label it too, wiring, 180, plastic. You can abbreviate a little bit if you like, that's okay. And now, let me go back, and it says each Terminator telephone uses 2 feet of wiring and 3 pounds of plastic. So the telephones are X. 2 feet of wiring. So for the wiring, and the telephones are X again, I'm going to have 2X, 2 feet of wiring for every telephone. Telephones are X, 2 feet of wiring, and 3 pounds of plastic. So plastic is here. So again, we're still dealing with the telephones. 3 pounds of plastic. So the telephones, which are X, use 2 feet of wiring, 3 pounds of plastic. So now let's go to the answering machines, which are Y. Each Mad Max answering machine uses 5 feet of wiring and 4 pounds of plastic. So again, answering machines are Y. So 5 feet of wiring. So in my wiring constraint, I'm going to have 5Y. And in my plastic constraint, 4Y. So again, the answering machines are Y. Each answering machine uses 5 feet of wiring, and each answering machine uses 4 pounds of plastic. Now they're going to have a plus, and the inequality symbol is going to be less than or equal to. If there's 190 feet of wiring available, you can use up 180 feet, all 190 feet, but you can't go beyond 190. The amount you use must be less than or equal to. You cannot use 192 feet of wiring because you just don't have it. So these are my constraints. Step 1, identify the variable. Step 2, write out the object function. Step 3, set up the constraints. Step 4, for each variable, you must include that it is greater than or equal to 0. So I have x and y. X is greater than or equal to 0. Y is greater than or equal to 0. So now we have a problem that we're ready to solve. So what I have to do now that I have my maximize and my subject to is graph the feasible region, label the corner points, fill out the chart, state my solution. So now what I'm going to do as I draw the graph, I'm going to use different colors. So my wiring constraint, I want to draw that on my graph, and I have the graph kind of set up. I want to pretend that the first constraint that actually says 2x plus 5y is less than or equal to 90, I want to pretend it's 2x plus 5y equals 190 and find 2 points that satisfy that if I pretend it's an equation. So I'm going to make my typical little x and y chart right next to my constraint, find 2 points that satisfy it when I pretend I have an equation. So first, I'll put in a value of 0 for x, and I have 5y equals 190. So I want to divide out the 5, and you'll see that it should come out to 38. So if x is 0 and y is 38, you'll have 190 equals 190. It makes the equation true. And next, I'm going to 0 the y, and I would have the equation 2x equals 190. So to solve that for x, divide away the 2, and you'd see that x would have to be 95. 2 times 95 makes 190 equals 190. So now, let me set up the constraint for plastic. Just because I can see the numbers I'm dealing with are getting fairly large, I want a good idea of what to run my number scale at. And right away at 95, I'm not going one at a time. So let me see what this one for the plastic comes out to. And I'll do that one in red. So let me make my little x and y chart next to that. Again, I'll go in red. So if I pretend it's 3x plus 4y equals 180, let me start by zeroing the x, and I'll have the equation 4y equals 180. So x would have to be y would have to be 45. 4 times 45 would make 180 equals 180, again, once you've zeroed the x out. And then, for a second point, if I zero the y, I have 3x equals 180. Divide out the 3, you'd have x is 60. Now, where I have a biggest value I'm going to deal with of 95 to determine what type of number scale I want to use for my graph, 10 at a time is a good choice. So let me label it by tens, and I can keep the x and y on the same scale. So I started the graph, but I didn't label the scale. So the y, I'll do 10, 20, 30, 40, 50. That's actually enough. My biggest y is 45, but I can easily just run it to 100. It's a natural spot to stop. You don't have to. And the x, I will also do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So now, the wiring constraint that I started to do in green, let me put that on my graph. So 1 point was 0 for x, 38 for y. So on my graph, if I go over 0 up 38, I don't have that on my graph exactly. My graph goes 30, then 40. So by eye, I'll estimate that 0.38 is over 0 and a little under the 40. Same thing with 95.0. I don't actually have 95 on my scale, but right between the 90 and the 100 would be 95. So just estimate it by eye reasonably. If I go over 95 up 0, I'll put a dot where I feel that would be. And let me connect that with a straight line. Now I have to determine whether I shade below this green line or above it. Now, to do that, I'll pick a test point that's not on the line. I like to use 0, 0. 0, 0 is not on the line. And for my wiring constraint, if I put in 0 for x, 0 for y, I get the statement 0 is smaller than 190. That's definitely true. So for my green line, my test point was on the underneath side. The result when I put it in was true. So my test point's in the shaded side, which is underneath. So everything underneath the green line is shaded. Now the plastic constraint, which I've done in red, one point to graph that is over 0 up 45, again, which is not exactly on my number scale, but just between the 40 and the 50, I'll estimate by eye that 45, I go over 0 up 45, and I put a red dot. And then the other dot to graph that would be over 60 up 0. Over 60 up 0. And I'll connect those two dots, and I'll make a red line. And now I have to decide if I shade below the red line or above it. Now, my test point that I like to use, 0, 0, is not on the line, so I can use it. And for my constraint for the plastic, if I put in 0 for x, 0 for y, I'll have the statement 0 is less than 180. Certainly true. So 0 is less than 180. My test point is on the underneath side. The result was true, so the underneath side is the shaded side. And I will shade under the red line. I won't even go above the green line because I know that can't be part of my feasible region. Now the last two constraints, x is greater than or equal to 0, which basically means you can't make a negative number of telephones. That wouldn't even make sense. And y greater than or equal to 0, you can't make a negative number of answering machines. That doesn't make sense either. So the x greater than or equal to 0 keeps you on the right side of the y-axis, only points with positive x coordinates. The y greater than or equal to 0 keeps you above the x-axis. And now the area that satisfies everything simultaneously, I will shade in red. And I do not go out into those little extra triangles. It's only the area that satisfies all the constraints simultaneously. This is the feasible region. This represents what combinations of answering machines and telephones that you can make with the amount of materials that you have available. Now what I have to do is label the corner points. So I have one out in the middle, and the others are along the edge. So the first corner point I have is over 0 up 40. I'll come right around. The next one is 0, 0. That's a corner point. Can't possibly be the maximum, but it is a corner point. The next corner point I have on my graph is over 60 up 0. That's a corner point. And I have one out here in the middle, which again, you can try and read off the graph, but sometimes it's not that easy. The right way to do it is take the two constraints that are intersecting, the one represented by the red line and the green line on my graph, the wiring and plastic constraints, and solve them simultaneously. So I have enough room up here. Let me just take this one and write it as equals 190. So the wiring constraint, I would have 2x plus 5y equals 190. And then the plastic constraint, I would have 3x plus 4y equals 180. Now, what I would like to do, I could go with a positive 6x, negative 6x and make the x's cancel, which would work. Or if I do the y's, I guess I would have to do positive 20y, negative 20y. That would work too. It would give me the same answer either way. Where I'm going to be dealing with slightly smaller numbers for the x, I think the x is going to be easier to deal with, so I'll choose the x for that reason. But again, same answer either way. So to make the 2x into a 6x on the top equation for the wiring, everything gets multiplied times 3. So 2x times 3 is 6x. 5y times 3 is 15y. And then 190 times 3 would be, I better check this on my calculator, it would be 570. Yes. Now, for the bottom equation, with the 180 for the plastic, I want to make a negative 6x. So I have a 3x now, so to make a 3x into a negative 6x, everything has to get multiplied times minus 2. So 3x times minus 2 is negative 6x. 4y times minus 2 is negative 8y. And then 180 times minus 2 is negative 360. Now, if I combine the two new equations that I've made, the x's cancel. Positive 6x, negative 6x, which is what I want. Then I have positive 15y, negative 8y, which would make 7y. And then equals positive 570, negative 360 would be positive 210. So if 7y equals 210, divide out the 7, you'll have y equals 30. So my point where my red constraint and green constraint intersect with each other has a y coordinate of 30. And according to my graph, that looks pretty reasonable. Now, what about the x coordinate? Take my y equals 30, go back to either of the original equations, and find the value of the other one. Doesn't really matter which one you use. It's probably about the same amount of work. Let me just grab the bottom one that has the equals 180 that was originally for the plastic and put in a 30 for y. So that'll be 3x plus 4 times y becomes 4 times 30 equals 180. 3x plus 120 equals 180. 3x equals 60. X equals 20. So the x-coordinate of the point where my constraints intersect with each other is 20, which by my number scale seems pretty reasonable. So now I've labeled all my corner points. What I'm going to do now is fill in my chart, which I should be able to fit pretty comfortably right here. So again, the chart is going to have 3 columns. The leftmost column, I will list my corner points. The middle column, which I leave wider, I'll put my object function, which for this particular problem is z equals 25x plus 28y. And the last column will be for output. And I have 1, 2, 3, 4 corner points, so I'll need 1, 2, 3, 4 rows in my chart. And I can list my corner points in any order as long as I don't miss any. So one is over 0 up 40. The other one is over 20 up 30. The next one is over 60 up 0. And the last one is 0, 0. And let's see what type of output I get from each one. So the first one, 0 for x, 40 for y. 25x becomes 25 times 0, and then 28 times y becomes 28 times 40, which should be, well, the 25 times 0 is 0. And let's see what I get for 28 times 40 is 1120. So 0 plus 1120 is 1120, 1,120. So now the next corner point has an x value of 20 and a y value of 30. So 25x becomes 25 times 20. And 28 times y becomes 28 times 30. So 25 times 20 should be 500. 25 times 20 is 500. And then 28 times 30, let's see what I get. 28 times 30 is 840. So 500 plus 840 is 1340, 1,340. And then 60, 0. X is 60, y is 0. Put that into the object function, and you're going to get 25 times x is 25 times 60, plus 28 times y becomes 28 times 0. So 25 times 60, I think is 1,500. Let's see, 25 times 60 is 1,500. And 28 times 0 is just simply 0. So 1,500 plus 0 is 1,500. And the bottom one, 0, 0, is easy. So 25 times x becomes 25 times 0. 28 times y is 28 times 0, which would give you 0 plus 0, which is 0. So now the possible amounts of profit we can make are $1,120 of profit, $1,340 worth of profit, $1,500 of profit, or $0 of profit. Well, you want the most profit you can get. So the last step, which is state your solution, I will put maximum profit of $1,500. And instead of saying at the point, we would say by producing So the point that gave me the 1,500 was 60, 0. The x value was 60. So the x is how many terminator telephones. So 60 terminator telephones, which I'll abbreviate a little bit, and no answering machines, 0 answering machines. So the end of this big problem is you can make a maximum profit of $1,500 by producing basically only telephones until you run out of resources. You'd eventually get this by some trial and error, but using the method of drawing the graph and finding the corner points,